All right, guys, well, welcome back, and we're now going to go over Chapter 3.3. I want to point out that our topic in this video are the derivative rules. So if you remember, I said we're going to take the limit of the difference quotient, okay, this guy here, and they're going to apply this guy to a bunch of different functions. They're going to do it to polynomials, our trig functions, our natural logs, and all the functions that we know and love, all the parents. And we're going to come up with rules, and you need to list those rules, like what do we do for polynomials? They're also going to give you rules for combinations. So rules for addition, subtraction, multiplication, and dividing of functions, sums of functions, combinations of different functions, functions that are quotients or products of two different functions, and so on. In addition to like polynomial, log rules, and so on. So you'll need sections for all of the different rules. I don't do the logic or the proof or the intuition. We just don't have time during summer, so there's no proofs during summer. Just the rules. We're just going to do the rules. I'm going to show you how to use them, and we're going to get you through the problems. Now, bear in mind, if you're into this kind of stuff, I have plenty of stuff in the shared folder. You want to get bored some night and go in there and read. If you look under derivative rules, you're going to find different things I've written up and stuff, and you can get bored and nerd out all you want. But during the summer course, we don't have time to talk about the why of these too much. I'm just going to show you how to do them. I'm going to teach you the algorithms, and you're going to memorize them. So add a page in your journal, your digital, written, however you do it, and make sure you have a section devoted to derivative rules. I would suspect it'll grow up to 15 pages when you're all done with it. Unless you're one of those micro writers, then maybe only 5. But somewhere in between 5 to 15 pages you want dedicated to building a list of derivative rules. Okay, so next up we're going to do 3.3, number 22. So let's go ahead and take a peek at that. And the first function we have is g of x equals e to the third. Now, a lot of students, you read all of this stuff about the power rule, okay? So at the beginning of this chapter, and you may have heard some stuff online or read about it online, is how do we do something? How do we differentiate something with a variable? And we take the n, we subtract 1, and we multiply it in front. If there's a chain rule, we multiply by du dx, but you don't know that part yet, so don't worry about that part. But this is fairly routine. So you just spend all this time with your book, and you come to this problem, and you're like, oh yeah, just like they showed me in the examples, if I have f here, I just multiply in front and subtract 1, and now this is going to be the derivative of the function f prime. And then people want to do that here, and then you get it wrong, and you wonder why. Okay, don't forget that e is just a number, or a constant. Don't forget that 3 is just a constant. So e is roughly equal to 3. Excuse me, 2. It's like 1.78 or something like that, right? So 2 to the third would be 2 times 2, which is 4, times 2, which is 8. So this function, g of x equals e to the third, is more or less 1, 2, 3, 4, 5, 6, 7, 8. It's just a horizontal line. Somewhere in there, okay? All right, we're going to say not to scale. Somewhere around in this area, right? Whatever it is exactly, you can put it in a calculator. The point is, it doesn't matter. This is just a number. This is just y equals some number, and that's a horizontal line. And a horizontal line has no rate of change. There's no change in its slope anywhere along here. So on that list of derivatives, make a big note that derivatives of constants are 0. So g prime of x, in this case, is going to equal 0. So it said to find the derivative is 0. And the derivative is going to be the function of this guy. Okay? And there we go. Excuse me. Yes. The derivative is going to be the change in slope of g of x. So this guy is the change in slope of g of x. And the change in slope of g of x, which the derivative, that's what the definition of a derivative does. When we have it in a function form, it gives us a function for all the changes in slope all along the line. There are no changes in slope here, so g prime of x is equal to 0, and that's our answer for 22. So again, you need to keep this list on your own. don't accidentally use the power rule here. So if I see this, okay, that's obviously wrong because you're using the power rule, but the power rule is only to be used when you have a function of x. Okay, we have a function of x present there. All right, so 22 is done, and let's do a nice, good chunk of examples here. I'm going to do 24 next. I'm going to take a sip of coffee. All right, so now we have 24, and we have g of w equal to 5, 6w to the 12th power. All right, so w is our independent variable, and so let's go ahead and jot down what our power rule is here. So I have it pulled up here, and I'm going to write down a simple way to write these. This is going to be a helpful list for you guys later, okay? But I'm going to write a simpler version here for you right now, but I do encourage you to find this file. It's called All Derivative Rules, and go through it with me as I'm going through it with you now. So a beginner's way to write this information out is now on your screen, which is the rule we're going to use here is that when we have a function x to the n, the derivative function is given by this number in front multiplied by x to 1 power less. So a good classic example would be x to the third. If x to the third was regular f, then it would be 3x to the second, and so on. So all of that work you did with this guy, okay, from the previous chapters, and if you're not staying up, go back and do it first. Every time you did this to any polynomial, it could have been this one, could have been this one, you know, any function you could have had. It could be you know, whatever you want it to be. It could be the 7th power, for crying out loud. But doing this on these functions is super long and super difficult. So they did this on this parent form, and they came up with this formula here. Okay, I'll briefly show you. I think my mouse died. Yep. Okay, I think I have a proof of that rule. Since I might hunt and peck a little bit, let me pause. And again, I'm not going to go through this proof. I obviously did this with students in the past, but this is what you need to do. I also showed a relationship between this and Pascal's triangle and presented on it at a conference. It was a pretty silly presentation, but I had fun. And anyways, you do some stuff like that, and it's from that you get this simple rule. But it takes all of this because, as you know, these problems were really cumbersome, and so to put it in function notation and to evaluate the patterns takes combinatorics and Pascal's triangle and factorials and all kinds of things. It's actually the simplest rule we have, which is the power rule. This is the first rule. Add this to your page of notes. Don't forget to add this to your derivative notes, okay? I'm going to even put here notes, okay? But this simple rule is the longest, most complex proof of all of them, in my opinion, and the hardest to get your head around. And that's why I wrote it out, because it was as a teacher, that's something that's fun for me, is to write that out. Doing this rule is very easy. Once you prove this pattern, this becomes easy. It's 12 times 5, 6, w to the 11th. We now cancel, and we get 10 w to the 11th for g prime of w. That's like the easiest thing to do in the world. And this is, again, I'm going to cross these out so that you don't confuse them with the rules themselves. This is a way to make flashcards or notes to remind you what to do anytime you have a polynomial. Okay? That's what we do with polynomials. So 24 is done. Let's now take a look-see at 26. All right, I'll replace my mouse batteries later. I want to keep the vibe here. So we have now f of v equals v to the 100th plus e to the v plus 10. So make sure that you wrote it out like I did, And we now want to do this. Now I want to note that you have a transcendental function here, and it's quite early in chapter 3, okay? And that's because your book is an ET version, an early transcendentals version. So students often ask, why is it called early transcendentals? Well, in books that don't have early transcendentals, you won't see the derivative of e to the v until much later in the curriculum. There's a kind of a split in the community on when and where you want to see derivatives of transcendentals. Do you want to see them at the same time as polynomials? Do you want to see them at a later time than polynomials? And the answer is, in early transcendentals, you have both. And in early transcendentals books, we see them just like the name suggests, early on. So, again, you have your derivative rules. Notes. I can't stress this enough. Okay? And your derivative rules, whatever page you're at, you want to write transcendental, or you could write exponential. Okay? And so e to the v, and this is the cool Schdazola thing here. Okay? If f of x is e to the v, the derivative is also e to the v. So it's super cool. It's pretty creepy. Alright, and there's lots of videos on this, and this is obviously why e is a special number that we use in the law of exponential change. Instead of just using an arbitrary base b to the x, we don't do that. That's not as good as using e to the x, so we don't do that. We use e to the x, okay, which makes things happy and has reasons inherent in how things grow that make it a more convenient thing numerically to use in terms of exponential modeling. And then it also ends up having these patterns as well make it a more convenient base to use because of the convenience of this derivative. If this is not the case, for example, for b to the x does not have a derivative of b to the x. It does have b to the x in its answer, but then it has some other stuff that fixes for the fact that it's not e to the x. And we'll get into that later. So the first thing we want to also add to our derivative list is the sum rule. And the sum rule is one of those arithmetic rules. So this is arithmetic. This isn't a derivative rule for a function. And the sum rule is that if you have f of x plus g of x, it's just going to be f prime of x plus g prime of x. Don't overthink this rule. Add it to your list. Definitely get it on there. But what that means is that I just do these derivatives separately. So 100 v to the 99th, this is like f of x. So here's how the sum rule. This one here is like g of x. This one here is like w of x or whatever. Like you can imagine that each of these are their own little independent functions and they're like micro universes. So it's a sum of this function plus this function plus this function. And so you do the derivative of this function plus the derivative of this function plus the derivative of that function. And the sum rule, okay, which is just f of x plus g of x is f prime of x plus g prime of x, is just telling you that. Add that to your list too. So we do this one, and then we sum it to the derivative of this one, which is just e to the v, and then the derivative of 10 is 0. The derivative of a constant, what's the change in slope on the y equals 10 line? So there's point 10, and y equals 10 line is a horizontal line. There is no change in slope. It's flat everywhere. So the slope of a constant, again, that should already be on your list, is 0. So there is f prime of v. If you want to make it pretty, you can. So here we have 100v to the 99th plus e to the v. That's our final answer. All right. So hopefully that helps. I'm going to just pause and make sure I didn't make any boo-boos. And we're completely good to go there. I just noted the rules because I'm teaching you. They happen to ask for the rules. So we use the sum. We use the power rule. Okay, the sum was to do the whole thing. The power rule was for that part. And then the exponential base e rule was for the other one, whatever they call that silly thing. Exponential e to the x rule for that. And there we go. And so that's done. Let's go ahead and head over to 28 and let's keep doing these for practice, and you guys do the other ones and we'll go from there. All right, So 28 is g of t equals 6 square root of t. Now, some books, so you have your derivative rules. Okay, you can, I would consider this one optional. And they even told you, they even kind of show you that it's kind of optional. And they show you that here with this little disclaimer here. Oh, hey, if you want the derivative of square root of x, look at this page. But that's not really an issue because this is just another polynomial. This is t to the 1/2 power, right? And so we can just do the power rule here. So you decide whether you want to list a separate algorithm for this. I never do it. When I'm doing calculus often, I have the pattern memorized of what it is, but I still just kind of sketch it out like this first and do it in my head. So by the power rule, this will just be 6 times 1/2, and then it's t to the 1/2 minus 2 over 2, and that's going to be negative 1/2, and t to the negative 1/2 means we're going to have, first of all, that cancels out to 1 and 3, means we're going to have 3 over t to a negative power. This whole thing equals t to the negative 1/2, and t to the negative 1/2 in the numerator is the same as t to the 1/2 in the denominator. Okay, and so we're going to have equals 3 over the square root of t. So for me, it's just easier to just do good old-fashioned power rule. Now, again, I don't have to write out that many steps when I do this in my head. I just literally do that in my head. But I'm writing out these steps. You need to probably write them out as you do these for the first time and begin learning these patterns. But bear in mind that the square root function, power rule, the square root of function is just a fractional power. So it completely works to just do good old-fashioned power rule there. So now that 28's done, let's take a look at 30. All right, we have f of x equals the square root of s divided by 4. So I'm going to do, the first thing I'm going to do is just a rewrite. I'm just going to move 1.4 here and just do that just to make it a little easier to visualize. The next thing I'm going to do, let's get my paper straight because it's all, I tend to write crooked. I can get the document cam perfectly aligned and then I end up reverting back to instinct and I mess it up. So I just straighten out the paper like that. All right, so what we're going to do now is to get f prime of x, therefore we're going to multiply by the 1/2 power. So I can write it again one more time if you want, s to the 1/2. All right, so we're gonna do the power rule on this guy, power rule on that guy. So it's going to be 1/2 that we multiply in front of everything, and then we're going to take 1/2 and subtract 2 over 2. Okay, 1/2 times 1/4 is going to be 1 over 8. And then we're going to have that same negative power here where this is going to simplify to s to the negative 1/2, meaning the square root of x is down here, meaning that making it look pretty now at the end, I just have 1 over 8 radical x. And so I think it's perfectly acceptable to just do the power rule here. You have plenty to memorize and race through during summer. Why give yourself another 2 rules to learn that aren't actually that helpful? That's my opinion. You do what you want. You're more than welcome to memorize that algorithm. I think that don't get me wrong, I have the algorithm memorized, but it will come to you with time. And when you're trying to keep a bunch of things straight and actually solve problems that invoke these rules, remember you can always do this because that will come in handy. All right, next up we have 62. So I'll write it big here. Leave it open for a little bit. Been forgetting to do that, sorry. One of these days, if we have a perfect world and I have time to do more editing, it would be nice to refine these. And I do understand that need, but it's like, it takes a lot of time to make the content, then do the thing, then follow up with you guys, then do all the grading. So, not complaining, I think I do a lot, and again, I hope you're benefiting from these videos. I know that it would be ideal to be able to ask me questions, and I'm stalling obviously for people to see the 62 if they're scrolling through the thumbnails and getting to where they need to get to. But let's work with me. We're doing the best we can. We can't always use the perfect tools for everything, And perfection's the enemy of the good, blah, blah, blah. All right. So, the derivative of a constant times of other function is just the derivative times the constant. And so I don't want to take too long on this, but this is the same as 1/4 times e to the x. And remember, to do the derivative of all of this, we're doing the limit of the difference quotient of this and this. And when we do that, we're doing the limit of the entire thing. But when we do that, by the properties of limits, this can simplify to 1/4 times, to 1/4 times this guy, okay, of just this part. Because when you do, remember the rules of limits. So when I do the limit of the difference quotient of this thing, okay, the 1/4 can be treated as a constant. Anyways, I said that really sloppy. The point is, I think even I kind of said it. I tried to say it simply, so part of what I said was wrong, but I think you get the idea. So based on the rules of limits, the 1/4 can be left alone, and we pretend it's not there, and we do the derivative of the e to the x, and it's because of the limit rule for constant multiples. Okay, and the constant multiple can be moved out to the front of the limit, and a derivative is a limit, so that's why the constants stick around. So the constant stays there, and I didn't talk about it with polynomials because students don't tend to get confused on that. So when we had things like this, you know, I just went like this and multiplied it, and you know, and so on. Students don't seem to get confused here, but they seem to get all wonky about the 1/4 on the e to the x. So hence I brought it up, and I'm just reminding you that both in this case and both in cases like this, when there's a multiplicative constant, 1/4 times this stuff, 1/2 times that stuff, because of the multiplicative constant rule for limits, that's why that just goes to the front. The derivative of e to the x is e to the x, so we literally have the same thing down here. I just wrote it a little differently. And then this is minus 1. And now, they want us to evaluate this at a equals 0, and to determine, we have two things to do. Find the tangent at a, use tech to plot both curves. So let's evaluate it at x equals a equals 0. So this is f prime of x, and that's, you found the derivative. Now we're going to find the tangent line using this. So plugging in x equals 0 to f prime, we get 1/4 e to the 0 minus 1. And of course that's 1/4 times any power to the 0 is 1 minus 1. And so all of this equals 1/4 minus 1, which is negative 3/4. And so negative 3/4 is what we get at point 0. Okay? Oops, I'm sorry. Yes, we do need this. And this is going to be our slope of f at x equals 0. Okay, so that takes care of that. What we also need is, we know the point is 0, but we don't know what point goes here. So we need to plug in 0 to the original as well to figure out the full point, not just the x part of the point. So if we do that here, we're going to get e to the 0th over 4 minus, and then we're going to plug in 0 for x, and we're going to get 1/4 minus 0, which is just 1/4. So the full point we had to solve for. Now that we have the full point, now that we have m, we can use these together to generate the equation of the tangent line, which we're going to do now. And we're going to use point slope form. So we're going to do y minus y equals m x minus x. And we get y minus 1/4 equals a slope of negative 3/4 x minus 0. Simplifying that out, we get y equals negative 3/4 x plus 1/4. We're going to plot this function, and we're going to plot, so this is the tangent, not the derivative, and we're going to plot the original function f of x, which is e to the x over 4 minus x, on the same coordinate plane using Desmos right now. But before we do that, I want to just bear in mind, what did we have to do here? You have to find the tangent at A. Okay, the tangent at A requires us to A, get the derivative, which we did here, and then to find the tangent, or the equation for the tangent line, we need to be able to put it into point slope form, which means we're going to need the slope and we're going to need the point. Okay, the point we get from f of x. The slope we get from f prime of x. To get this value, I plugged in 0 to f prime, and that gave me the slope that I put here. To get the ordered pair that we're using, they told us x, the x value of the ordered pair was 0 in the original problem. To figure out the y value, which we had to use here, I plugged in the value they gave us to the original equation, which gave us that value. Once we have both of these equations, okay, we can now go use technology. You can take a screenshot and throw it into your document with Word. You can use GNU plot, you can use Wolfram Alpha, whatever you want to do. Just give me a screenshot of that and you'll be good to go. Whatever graphing tool suits your preferences. And once we do that, we see that we have the nice red line here, which is our tangent line, and it is tangent right at that instant of 0 there. You can see just from the smushy, smeary closeness here and the smushy, smeary closeness here that it's equally symmetrical. There seems to be about the same amount of smushy smeariness on either side, and it's touching right, it's coinciding, it's overlapping with the line at that point because of our degree of resolution. Of course, if we could zoom in, it would only be overlapping at that exact point if they were 1 point of width small, I believe, right? I think that's right. You get my point. So we can see the tangent line, which this line has the same slope that this black function here has right at that instant at x equals 0. So we've confirmed it with technology, and we're ready to move on to 64 and call it a set. And that'll be the end of this set, and then we'll do the derivative worksheet in 3.4, which is the last chapter for this week, in the next video. All right. So 64, and I will make sure to stall. Let's get it queued up here. And we'll leave this open. And I'll just slide that over. All right, and I'll start reading it while I leave it there. So find the slope location. So f of t equals blah, blah, blah. It's a cubic function. Find the values of t for which the slope of the curve y equals f of t is 0. Okay. Find the values of t for which the slope of the curve is 21. All right, I think that's a sufficient amount of time to leave this up. Let's go for it. So if we have f of t equals t cubed minus 27t plus 5, what we're going to do here is do the derivative of each of the terms. So the derivative of that, we multiply the 3 in front, subtract 1, and we get this. Okay, the derivative of this guy, remember 1, we're going to multiply the 1 in front. 1 times negative 27 is just negative 27, because 1 times anything is itself. And then 1 minus 1 equals 0, and t to the 0th is just 1. So if you want, you can write it in a times 1 there if it makes you feel better. Used to when I was starting, and I still don't mind writing it in every time just to prompt myself visually when I'm debugging lines of math. And then derivative of 5 is a constant, which is 0. And what we're doing here, this whole swath is sum and difference rule. And then within our sum and difference rule, we're doing our power rule, and power rule 3 times. So we have an overall arithmetic rule, because each of these could be like its own function. And we have a difference of 2 functions and a sum of another function. And by the associative and commutative rules, you could go in multiple directions there. The point is it doesn't matter. It's interchangeable, that you could just do the derivative of each sum or difference individually and drop them down and follow your signs, and you're good to go. So we now have that the derivative f prime of t is given by 3t squared minus 27. And now what they asked us to do for 64 is to find, and this is the slope machine. Why did I want that? Well, they asked us to find the values of t for which the slope of the curve y equals f of t is equal to 0. Well, I needed to make my slope machine of f. My slope machine of f is f prime of t. Now I can have 0 here equal to 3t squared minus 27. I could say, when is it equal to 0? And I get 27 equals 3t squared. I'm going to divide that 3 on both sides. This side will be 9. And I'm going to get that t equals the square root of 9. Again, when you write the square root in your math, that means it's going to be negative 3 and positive 3. Sorry, there was some noise outside. And so we're good to go. So negative 3 squared will be 9, positive 3 will be squared will be 9. And so you do plus or minus of each, you get your negative 1 and your positive 1. And again, that's because when you do the square root, when you write the square root in algebra like we're doing here, both roots are always implied. Now you may have other restrictions that exclude one or the other. In this case, you don't. This is telling us that on the graph at 1, 2, and negative 3, and at 1, 2, 3, there is the same slope of 0. So somewhere along here, it's totally flat. And somewhere along here, it's totally flat. So we'll plot this guy at the end, and we'll take a look at what that looks like. And we probably know from Descartes' rule of sines that this is a t cubed with a few humps in the middle. So it's probably like that, and then like that, or something like that. So there would be the 0, and there would be the 0. Okay? You have one hump because you got negative and positive here by Descartes' rule of sines. So that's kind of interesting, and Descartes' law of sines, or rule of sines, whatever it's called, that's a thing that you need to know for curve sketching as well. And so we just did part A. And so part A would be these values down here, and you'd put part A or something, you'd show me some work, and then tell me where part A's final answer is listed. I can check your work if I need to. Now, to do part B, we need the same function machine. So we're going to use the same machine, but just set it equal to 60. Now we're going to add 27 to both sides, giving us 87 equals 3t squared. Let me just make sure I didn't do a boo-boo there. Yep, that looks good. We're going to divide the 3 out on both sides. What is 87 divided by 3? It's too late. I'm going to just make sure. Oh yeah, that's nice and clean. And we're going to get 29. I do that right? 27, 60. Yep, 60 and 27 are 87. That looks all good. And I get t squared equals 29. So I get t equals the square root of 29. The square root of 29 is going to be in between 5, which is 25, and 6, which is 36. And 29 is 4 this way, and 36 is 7 that way. So this will be roughly like 5.3-ish. And the only reason I bring that up is so that you understand what's happening. What's happening is that we don't know exactly what the scale is, but at 0.5, way over here at x equals 5-ish, 5.3-ish, the steepness of that slope there is 60, or the rate of change at that instant on the curve. The steepness of the tangent line would be. And over here at negative 5.3-ish, okay, the negative of that root that we just found, this slope is the same thing. And that makes perfect sense because cubic functions they're symmetrical here. The same way in which these slopes are decreasing as they go up, these are increasing as they go up. So that means that at one instant, they will have a change that's identical on either side and either branch. And then those identical moments will just continue like this. And so you're always going to get those out in pairs, and that's always because you're going to have, in a cubic function, its derivative is going to be a square. So you're always going to have two solutions for where a slope is a certain thing, reflecting those symmetrical growth patterns that we see present on t cubed. So that's our next answer. Don't do that. Don't put 3, just leave this as your answer or use a calculator. I was just doing this to plot and get us a quick picture of what's going on. Okay, but don't you dare like do this is called interpolation. Okay, no interpolation in here. You do everything precise up to thousands, and I've told you that already. So now what we're going to do is we're going to plot this function in Desmos, and we're going to look at the patterns that we just noted in this problem. We're going to come back and look at those same things that we located in this problem. And when we do that, I had to adjust the scale factor a little bit. Let me actually toggle one more of those. Let's make the x factor shorter. Let's do like 25. I think that'll be sufficient. Yeah, we could even do a little bit more, but this gives you the general idea. And so let's go back to what we learned. So let's keep this plot in mind while we're looking at our work here. So we found that slopes of 0 exist at -3 and +3. And you can see right here, 1, 2, 3. I come down and there's a slope of 0. And I go 1, 2, 3, come up, and there's a slope of 0 right there. What else did we find? Well, we found that at square root of plus and minus 29, we have slopes of 60. Okay, slopes of 60. When does 60 equal the derivative? 60 equals the derivative when we have this value. So at this point, we'll go over here and go to Wolfram Alpha and actually get our value of what the derivative is. Excuse me, not the derivative, the root. So 29, let's get the exact value here, is 5.38. Darn, I was pretty good at approximating there. So 5.385. And let's go ahead and, where's my Desmos? Okay, Desmos is there. And let's make this bigger. And so at 5.3-ish right here, yep, all I know is that when you're looking at 60, you're expecting really steep. And that's already really steep. You know, if it was like down here, I'd think, did we make a mistake or something? That doesn't seem like a slope of 60 right in here. But it's just really steep. Now, if you wanted to, you could go, you know, this is 5 to 6, so that's 1. And then you can see this is 0 to 50. That's 50 right there. And you can see you're not quite at it. And if you look really closely, it actually hits it right there. So you can see that this segment of this curve right here to here can be approximated by this triangle. Right there, the width, and this vertical line up. And it's like almost like there's a triangle there. And that triangle there, which its peak is right here, and it goes down to here and over to here, that triangle has a rise over run, a hypotenuse with a rise over run of 60. So it sure looks good to me. It looks like everything we did is right. Of course it is. I'm just showing you how you can visually confirm. And you see the same triangle here, okay? Very similar pattern, all right? But it's shifted over because it doesn't go exactly through 0. So you're not going to see it exactly the same way you see it. Actually, this one starts here and then goes to like there approximately. And that's the 10 here plus the 50 here for a total of a triangle of 60. So we could see all along here, it's really close to 60. And that means that our value of -5.3 is exactly where it is, 60. But we have visual confirmation that what we found is realistic, and we've confirmed it visually. So everything seems to add up. And you should always do that. Remember that rule of 4 that we talked about? We want to visually confirm things. So your answers are pretty trivial in this case. You're just going to have 2 answers like that, and make sure that 64 points to those, either on technology or handwritten, however you prefer. And we're good to go. So that is now, this section's done too. And then 3.4 and the derivatives worksheet will be the next video that I do. So these 2 are out of the way, and we'll see you the next time. Bye, guys.